Hey guys, welcome back. We're moving into one of my favorite topics, which is electricity. Specifically, for this one, we're talking about electrical charge. And so you might have seen this, especially if you're like shopping for food and you're walking along with your cart, and then maybe all of a sudden you feel a shock. Uh, this is why. It's because of electric charge. So we'll get into this a little bit. So all material objects are composed of atoms. So we know this from chemistry. And so the next few slides are going to be a review of chemistry. So I'll go through these kind of fast. So we have atoms. Okay, atoms have protons and neutrons in the nucleus, as shown in the picture. On the outside of this nucleus, we have electrons on the outside. So we see protons have a positive charge, neutrons have no charge, and electrons have a negative charge. So like we talked about in magnets, if you have something that is the same pole, positive, positive, or negative, negative, they're going to repel, they're going to move away. As opposed if you have unlike charges like positive and negative, opposites are going to attract, they're going to move towards each other. So we find that most of the mass of an atom is because of protons and neutrons, which are in the nucleus. Okay, they're much heavier. Electrons, on the other hand, are lighter and are towards the outside of the atom. So if the nucleus contains protons, which are positively charged, and like charges repel, why does the nucleus stay intact? So we find that we have a strong nuclear force. This force attracts neutrons and protons to each other, but it only works with small distances, 10 to the negative 15, very small distances. We find that this is the strongest force in the universe so far, but remember, it only works for short distances. We also have another type of force called the electromagnetic force, and this force binds electrons to the nucleus. It is attraction between positive charge in the proton and negative charge on the electron. So what keeps the nucleus bound together and how? So what keeps the nucleus together is the strong nuclear force. What force keeps electrons bound to an atom? So the force that keeps electrons bound to an atom is the electromagnetic force. This attracts the positive and the negative. So protons and neutrons, they're very difficult to be removed or be disturbed. This is in the nucleus, so the nucleus is very strong. Electrons, remember, on the outside of the atom, they're going to be weakly bound. That means that you could take away or add electrons easily. So because electrons are weakly bounded, right, like we just said, they can be removed or added through events. So this is where static electricity comes in. It is any imbalance in either positive or negative charge. So when we say something is charged, that we mean that it's charged either positively or negatively. They're not zero. Okay. So electric charge is a property of matter. To have charge is a property, and the only charges you can have is positive and negative. The unit for charge, we call it a Coulomb C, and this is named after the French physicist. So most matter is neutral. It has no charge. So for example, let's say we have an even amount, positive charge plus 8, and we have negative 8. Of course, that's going to cancel each other out, and the charges are equal. There is no charge. It's neutral. So as opposed to something that is charged, let's say for example you have positive 6 and you have negative 10, and of course that would equal to negative 4. That means it is charged with a negative 4 charge. So if you ever rub a balloon on your hair, what happens is that you're transferring this charge. Electrons are transferred from your hair to the balloon. So now the balloon is charged. So this is called charging by friction. So that anytime you're, for example, you could also rub your socks on the floor on carpet, and you'll create electric charge. So you have this electrically charged balloon. Okay, when it comes in contact with the wall becomes polarized. That means that all the positive ends of the atoms in that wall are going to be attracted to the balloon. Okay, And so we have negative and positive attraction. So explain the difference between an electrically charged and a neutral object. So when we have a neutral object, obviously charges are equal. There is no charge. So it becomes available for something to be charged. Um, for example, the balloon. The balloon in the beginning was neutral. Then you transferred electrons from your hair to the balloon. Explain how there can be charge inside matter, yet the matter is electrically neutral. So we kind of talked about this already. The balloon was neutral, and your hair had electrons, and those electrons were transferred. So now we go into the Coulomb's law, and this is the math where the math is going to start coming in. The force between charges is very strong. Remember, force is in newtons and is extremely large number. This is a weight of 3,000 million cars. The force between two objects depends on two things, the charge and the distance. So depending on whether the charge is small or big, or distance is far or near, that's going to affect force. So when two charges, we say Q1, Q2, are separated by a distance r, as shown in the picture, there's a force. So these two charges are exerting a force. So it can also be two positives or two negatives. It does not have to be positive and just negative. So force is inversely proportional to the square of the distance between the charges. So that means if distance is increased by a factor of 2, force will decrease by a factor of 4. Because the square of the distance, if we take the square of a distance, that is equal to 4. So force will decrease if distance is increased. And that makes sense. The farther apart, let's say for example, you hold two magnets together, that's going to be way stronger than if you hold them, arm's length or even farther than that. So the more charge we have, the more force. The less distance, the more force. So when we say the less distance, we mean the closer they are to each other. The closer they are, the stronger the force, the stronger the attractions. Okay, so that makes sense. And then the farther apart, the farther you pull them apart, the less force. So force is directly proportional to the strength of each charge. And so here we have the equation, the first equation that we'll be working with, Coulomb's law. F, force is going to be in newtons. The constant K will always be 9 times 10 to the 9th. Newton per meter squared per Coulomb squared. So this number will always stay the same no matter what. Q1 and Q2 are the two different charges, and that remember that can be two positive, two negatives, positive and negative. And then R squared is the distance between them in meters. Okay, so let's say for example you have two steel marbles and each is given a net charge, so each has a charge of 1/1000th of a Coulomb. So Q1 is going to be 0.001 Coulomb, and Q2, the other charge, will also be the same thing. Calculate the size of the force, so we don't know force, on the marbles if they are held 2 meters apart. So we know R is equal to 2. Okay, so now we have all this information and we can plug it into our Coulomb's law formula. So remember, F is equal to K, which is a constant, Q1, Q2 over R squared. So K is the constant, it's always going to be the same, 9 times 10 to the 9th. That's always going to be the same, 9 times 10 to the 9th. Q1 is 0.001. Q2 is also the same value. And then we divide that by R squared, so 2 squared. When we put that in the calculator, we see that we get a force of 2,250 newtons. Okay, so on the next part, we're still working with the same values, but now it says calculate the size of the force when they're held 4 meters apart. So what happens to the force when I have them further apart? Okay, so we have a Coulomb's law, K, Q1, Q2 over R squared. So we know K is a constant, always the same, 9 times 10 to the ninth. And Q1 is 0.001, same as the other problem, and Q2 is also the same value. But now R squared is not 2, it is 4. 4 squared. So we see that when we plug this into our calculator, when you plug it into the calculator, you might want to separate it. You might want to do the top values first, 9 times 10 to the ninth times 0.001 times 0.001, and then divide by 4 squared, which is just 16. So we find that our force is 562.5 newtons. And so what happened to the force? If you notice in the first problem, our force at 2 meters was 2,250. And all of a sudden I increased the distance was farther apart, and the force decreased. So we saw this, we knew this, that when we pull those charges apart, force decreases. Lastly, we have another part of the problem where we're calculating the size of the force, but now the charges are different. So Q1 is 3 coulombs, Q2 is 4 coulombs, and R, they're 500 meters apart. Calculate the force. So force is equal to K, which is a constant, never changes, Q1, Q2, the charges, divided by R squared, which is the distance. K is 9 times 10 to the ninth, and our first charge, Q1, is 3, second charge is 4, Q2, divided by R squared, which is 500 meters squared. And so when we put that into the calculator, we obviously, because we have so much distance, but now the charges are increased, we have a 4.32 times 10 to the 5th newtons of force. So the first few problems that we did are with Coulomb's law, as far as figuring out different charges and different forces. There's going to be other type of calculations, as the one shown here, where we have to calculate what happens to the force when something else happens. So when we use this, we have a reference. F is equal to K Q1 Q2 over R squared. And for our reference, we say everything is 1. So we don't need to worry about K, because K is always going to be the same. Don't worry about it for these problems. Q1, Q2 will be 1 and 1, and R squared is 1. So that means everything here is 1. This is our reference. This is not the answer. This is our reference. So how are we gonna, whenever we get a new problem, this is our reference. So what happens to the force between two charges if the distance between them is quadrupled? To quadruple something means that you're going to increase it by 4. So notice that the charges Q1, Q2 are going to maintain their 1 value because it did not change. But the distance quadrupled. So now it's 4. Remember, don't forget to square it because that's part of the formula. So 1 times 1 is 1, 4 squared is 16. So what we find is that if the distance is quadrupled, if we increase the distance, our force decreases. So you notice it decreased by a factor of 16. So here's another type of problem. What happens to the force when one charge is doubled? So it's increased by 2, and the other is tripled. That means it's increased by 3, while keeping the distance the same. So remember our reference is 1, which is F is equal to 1 squared. That's equal to 1. So you should always have that as a reference. Now what happens if I change the charge of 1, which, remember, these are the charges Q1, Q2. 1 is doubled, 1 is tripled, and the distance, remember, is on the bottom, and the distance stays the same. So I'm going to keep that as 1 squared. So 3 times 2 is 6 over 1. So what happens? So when we increase charge, that increases the force.